Hello students, today we are going to start with this new chapter which is magnetic effects and the magnetic properties of material. So basically we are going to discuss how various types of materials possess various magnetic properties. And see, magnetic properties not just like behaving like magnets. You know what magnet is? Magnet has a property to attract iron particles. It has a property to exhibit its own magnetic field. But not all the materials can exhibit such properties. Some materials do have very feeble properties, some materials have very strong properties. So we are going to discuss all of that. First of all, we'll start with magnetic fields. So what exactly is magnetic field? Suppose I say that this is a magnet and this is its magnetic field. So magnetic field is that region or space about a magnet within which its magnetic properties can be experienced, within which its magnetic field can repel or attract some ferric particles, right? Or in very simple words, within which its magnetic force can be experienced. So this is what magnetic field is. Now how this magnetic fields came into existence and how it all started, for that you should know the bigger picture. I'll start with that Earth also has its own magnetic properties. So see, Earth has its own magnetic field. I'll give you a very good example of a phenomena which will show that Earth has a magnetic field. Have you heard about solar wind? Okay, if you have not heard about solar wind, have you seen aurora lights in pictures, not in reality, because it is exhibited only in the sky of North Poles and South Poles. So solar winds or aurora light, these combination causes aurora lights. How and what exactly happens is, see, suppose this is Earth, this is Earth's atmosphere, right? Now suppose this is the size of sun, because we are viewing it from a very large distance. From the sun, huge explosions, because sun is basically running, its energy is actually coming out of nuclear reactions, exactly. So nuclear fusion reactions is taking place. So lot of nuclear explosion is taking place on the surface of sun, and these explosions, they cause huge emission of very highly charged particles. So these particles, I will not go into much detail, these highly charged particles sometimes are referred as solar winds or cosmic rays as well. So these rays are continuously projected towards Earth. Now if these rays can penetrate the surface of or the atmospheric surface, it will cause a global catastrophe, because these rays are very highly charged and very energetic particles. They can cause mutations like what gamma rays does for the human skin. So our atmosphere, what it does, due to the magnetic field, suppose the magnetic field of our Earth is like this, north and south, okay? So this will be the north to south magnetic field. So these cosmic rays or so-called solar winds are deflected through this magnetic field, and they enters the Earth region only through the North Pole and South Pole, where the density of electric lines of force are maximum, where this magnetic field is maximum. So these rays, they enter the atmosphere from the North and South Pole, and that is why when these particles strike the particles of our atmosphere, they emit energy, and this energy falls in the visible region. So that is why we are able to see the light. So this is what aurora lights is all about. Now look at the picture. This diagram shows that Earth has a magnetic field and it's oriented from there to there, right? Like it has been referred as North Pole, it has been referred as South Pole. But I'll tell you something. Again, we are taking the example of this Earth's surface. Let's say this is Earth, and suppose this is my compass. Now I want to know where the North Pole is. The red part of the compass needle always points towards North Pole, right? So if it is North polarity needle and it is pointing towards North, how can this be possible? Because North and North are going to repel each other. Like same poles never attract each other. We know this phenomena when we were small. So thing is that this shows us something else. This shows that Earth does not have its North Pole on the northern hemisphere. Basically it has South Pole. That is why the North polarity needle of a compass points towards the geographical north. That is, the magnetic south lies on the geographical north, and vice versa. Magnetic north lies in the geographical south. Okay, I'll read it out. The earth itself has a huge magnetic field as if it had a huge bar magnet embedded at its center. The earth's magnetic field lines emerge from near the geographical north pole. It is near to, not exactly on the geographical north pole, it is near to. Why? Because if this is earth, this is the geographical meridian, that is geographical line passing through north and south, then magnetic meridian will be inclined at some angle. The angle is very small though, but it is inclined at some angle with the geographical meridian or geographical axis. So there is an inclination of that angle. Now, so these magnetic field has emerged from near this geographical north pole and re-enter at the south pole. The nature of the field around the earth varies in both strength and direction at various places on earth. The earth's magnetic field is strongest at the magnetic poles, that is the north pole, south pole, and it is weakest near the equator. Okay. Now, why does earth have a magnetic field of its own? Because the core is filled with ferromagnetic material, which is what? Iron and silicon. Now, why does these elements like iron and silicon are called ferromagnetic and they have more magnetic properties? To understand that, I'll explain you something, then we'll link it with the huge picture or the bigger picture. I am starting with the very basic phenomena, very smallest part which you already know. In our magnetic effects of current, there was this Ørsted's experiment which showed us that current carrying coil or current carrying wire produces its own magnetic field. That means, suppose this is a wire carrying current in this direction, then according to right hand thumb rule, there will be direction of magnetic field about it. It will be originating from this and it will be entering this region, right? This was so simple. This phenomena or this experiment showed us that current, if it has a magnetic field, then what is current basically? Current is actually what? Moving charge. So moving charge has what? Magnetic field. Now I hope this much part was simple, that moving charge has a magnetic field. Now everything which is made up of atom has what? Electrons rotating in the orbits. Now electron is a negative charge, and if electron is rotating or revolving, you can say, so if it is revolving about what? Nucleus, there is a moving electron. Electron is a charge and it is moving, that means it constitutes a current. So the nucleus part and this electron which is revolving about the nucleus, this is a moving charge, that means it constitutes a very, very, very small current. Okay, so this current, what is current? Current is charge. How do we define current? Rate of flow of charge, right? So what charge is flowing? Electronic charge, and rate of flow of charge upon t. T is the time period of this revolution. I can find out this time period by, time is distance over speed, so 2 pi r over speed with which it is revolving. So this gives me EV over 2 pi r. This is the small current, right? Now another thing which we learned in magnetic effects of current was, current carrying loop behaves like a magnetic moment or magnetic dipole. What was that thing? Suppose this is a loop carrying current I and it has an area A. So that means it will have a magnetic dipole moment of I times A. Similarly, if we have a current and it has some area of revolution, so this I times this area will give me small magnetic dipole moment, that is this much into pi r square. What will I get? Pi cancels out, this r cancels out, I get EVR upon 2. This is the small magnetic dipole moment associated with one electron which is revolving in a orbit. That means there are so many electrons which are revolving about a nucleus. That shows us there will be some magnetic moment associated with the combination of all those magnetic dipole moments, and hence it makes a dipole, very, very small though, but it makes a dipole moment or it makes a magnetic dipole there. Now we are talking about only one atom with these things in picture. Consider everything is made up of so many number of atoms, so how large that overall magnetic dipole moment would be if all the individual magnetic moments are combined together. But there is a big but here, that is, not each and every dipole moment gets added up because they are not in sync with each other. Actually what happens is, some of the magnetic moments, small magnetic moments, are in this direction, some are this, some are this, some are that, so they are in random directions, and that is why they do not add up. So they cancel out each other's effect, and hence net magnetic moment, if it is some left, is very small. So this gives the origin of magnetism within the bulk properties of matter. Now I hope this point is very much understood to you, that magnetism already exists within atoms, and if it is in sync with all the atoms, then it will create a net magnetism. If it is not, they'll cancel out each other effect. Now let's go through them. So I started this topic with that Earth's core is comprised of what? Ferromagnetic materials like iron and silicon, and they have these magnetic moments which are inclined towards each other. They are in sync, so they get added up and they create huge magnetic field. That is it. So now, the Earth at its center, a dense liquid core of about half the radius of Earth with a solid inner core. This core is thought to be mostly made up of molten iron and nickel, perhaps mixed with some lighter elements. Circulating ions of iron and nickel in highly conducting liquid region of Earth's core might be forming current loops and producing Earth's magnetism. Now this is just a theory. Actually lot of theories have been proposed for the magnetism of Earth, and most of them are considered true. So you can go with any theory which is considered in nature these days. Now the Earth's magnetic field, which I told you, is not parallel to the geographical axis, it is actually at some angle. So if this is geographical axis, it is at some angle. The angle is about, this is it's written 11.5 degree, but it's actually I think between 8 to 12 degree, because it varies at various places. So this is geomagnetic north pole, that is, this is geographical pole, and this is geomagnetic north pole. So now you understood what is geomagnetic north pole, where south pole exists basically. So this is geomagnetic south pole, right? And the magnetic equator and geographical equator, they are also like this. This is geographical equator and magnetic equator is like this, because of the variation due to places of Earth and the distance of the core from the surface of Earth, because that is something also which varies at various places. That is why. Now, magnetic elements. What are magnetic elements? There are few quantities which you should know to tell the magnetic field of Earth at a place. For example, right now if I am standing in Chandigarh, you need to know few things like magnetic declination and magnetic inclination or magnetic dip at Chandigarh to know exactly what magnetic field of Earth here is. So to understand that, let's start with magnetic declination. See what magnetic declination is. Suppose this is a magnet, I freely suspend it, it is free to move anywhere. Okay, now ultimately a magnet inclines itself with the magnetic field of Earth at that place. So whatever or in whichsoever direction the Earth's magnetic field is here, this magnet is going to incline itself in the magnetic field direction. Obviously opposite to it, because its north and south has to attract the south and north, right? Now the geographical north-south of this place might be in this direction. So there is some angle between them, right? So this is what magnetic declination is. It is the angle between magnetic axis and geographical axis at any place. Second one is magnetic dip. It is also referred as angle of dip or called magnetic inclination. What this one is, again, this is my compass. The black tip is our north polarity needle and it is pointing towards north, let us say. Now, if I suspend this compass in horizontal direction, or actually in vertical direction, this needle is going to point somewhere towards Earth. You can do this experiment at your place. So it is going to point anywhere towards the Earth, because the net magnetic field which is originating of the Earth is from the core. So it is going to direct somewhere towards the surface. The angle which this needle makes with the horizontal line, which is this line, the horizontal line, any horizontal line from that needle point, this angle is called angle of dip or magnetic inclination. So these are two magnetic elements which you should know. The magnetic declination, it is basically the small angle between magnetic axis and geographical axis at a place, and the second one is the angle of dip. It is the angle which the magnetic needle makes with the horizontal. Now we'll move on to next part. The thing I was telling you at the very start of this lecture was the small magnetic dipole moments or these small magnetic dipole moments add up together to form magnetic domains. So magnetic domain is basically culmination of few magnetic dipole moments. Now again, these magnetic domains might not be in the same order. If this arrow, this arrow, this arrow and this arrow, if they would have been in same order, that means they are actually adding up, but they are in various directions, they are in random directions, they are somehow killing their each other's effect. So atoms themselves have magnetic properties due to the spin of atoms electron. The group of atoms join so that their magnetic fields are all going in the same direction. We are now talking about magnetic dipole moments getting added up, called magnetic domains. Now these magnetic domains, if they are all inclined in the same direction, will cause the net magnetism. These areas of atoms are called domains. When an unmagnetized substance is placed in a magnetic field, the substance can become magnetized, though this is very temporarily, because see, in the last diagram, they are in random directions, but when this thing is placed in an external magnetic field, they all magnetic domains got inclined in the same direction. Now this material is going to possess magnetic field, but this whole effect is temporary. Why temporary? Why are they in this like same direction at this point? Because of external magnetic field. True, but the external magnetic field, if it is removed, then this property will possess a quality which is called elasticity. Now this elasticity is going to make all the domains fall back to their original position, though it might be a slow process, but gradually they are going to fall back to the original points or original places. So that is why this type of magnetism resides in a body, but it is temporary.